All right, now we're going to practice. We talked about the idea of half-life, the amount of time it takes for half of a radioactive material to break down into its stable product. And that gives us the age of certain samples of radioactive elements. So we can figure out the age of either animals in the past or rock layers or even meteorites or asteroids. So we're going to practice some things today, give you a chance to look at this, and hopefully after this process you can get a better handle on how it all goes together. So we're going to start with question number 1. Obviously, it's a very good place to start. All right, so it says, the diagram below represents the present number of decayed and undecayed atoms in a sample that was originally 100% radioactive material. So let's back up. At one point in time, all of these boxes were radioactive. So the question is, how many were there and how many are still radioactive? Well, there is 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6, 7, 8. So that 4 times 8 is a grand total of 32 boxes. So how many are still radioactive? 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 32. If we were to reduce that fraction, it is 1/4 or 25%. So 25% of this material is still radioactive. Now, if we were in class and I had you guys as a group, I would have shown you this. Now I'm going to zoom out so you see the whole thing. This here, that's in. Too close, too close. Hey, there we go. All right, so this right here is my handy-dandy, high-tech, radioactive half-life simulator. Now, actually, it's just a couple pieces of paper, but with some very important things written in a very important way. So this is what we're going to kind of illustrate here. This yellow paper on top is our 100% radioactive material, or 0 half-lives. This is our time 0. This is our starting point. So if we start that clock, time will go, and after 1 half-life, the ratio is 50% stable product, 50% still radioactive. Okay? And that's that idea of half-life. Half of the material has now decayed into a stable product. All right, now time continues. After the same amount of time that the first one took, the second one's going to take the same amount of time. And now we're going to be down to 2 half-lives. We have 75% of the material is stable and 25% is still radioactive. Time continues. We add another 12.5% after the same amount of time. Remember, it's the same amount of time to go from here to here to here. That's the definition of a half-life. Now, this is now 87.5% stable, and 12% is still radioactive. Time continues on, and we get to 4 half-lives. Remember, each fold here takes the same amount of time. Now we're up to 93.75% is stable, and 6.25%, I know that's really hard to read because my large marker doesn't work in small spaces as well, but 6.25% still radioactive. And I could fold until I couldn't fold anymore, half and half and half and half, and that would continue like the activity I finished the last part with, where you saw the dots go from blue to red, and that graph get created. Okay, so we want to think about these ratios as we move along. So again, I'll go through it one more time quickly. 100%, 1 half-life, 50-50. 2 half-lives, 75-25. 3 half-lives, 87.5, 12.5. 4 half-lives, 93.75 and 6.25 still radioactive. All right, you're going to see pictures that look similar to this in a short bit on this activity. So keep this in mind. Go back through if you want to rewind the video and look at this again to see how it breaks down. It might help you moving forward. All right, so let's go back to that first question now that you've seen that. So first question, got to zoom back in. Gave us a ratio of 1 to 4 or 25%. Now, if we remember, 25% still radioactive, okay, equals 2 half-lives. 2 half-lives. Remember the folding? 1, 2. So it says here that this sample has a half-life of 1,000 years. Well, if we've gone to 2 half-lives, it's 2 times 1,000 equals 2,000 years. And I just got to move that up just a little bit. There we go. So, looking at our answers, we're looking at answer letter B. Okay? So again, we're looking at the fraction, the relationship here. All right? Now, I've got to zoom back. Oh, wrong way. I keep getting these backwards. All right, the next question. So, which graph best shows the radioactive decay of carbon-14? Now, remember, this is an exponential decay. Okay, decay means negative. If you have a tooth that hurts, it's because you have decay on it. So that isn't a positive, that's a negative. So you want to think about it decreasing exponentially, which gives us an answer of letter D. Okay, answer of letter D. Moving on. These next 2 questions are very similar, but they show a different way of illustrating the same concept. So, it says here, the table below gives information about the radioactive decay of carbon-14. Part of the table has been deliberately left blank for student use. Half-life, 0, 1, 2, 3, 4, blah, 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 blah. Mass of original carbon-14 in grams, 1, half a gram, a quarter gram, an eighth of a gram, a 16th of a gram, and so on. Okay? Now, it says, after how many years will 1/128th of the original carbon-14 remain? All right? Well, first things first, notice in each one of these examples here, the fraction is getting smaller by a figure of 2, meaning we're doubling the denominator in each of these. So this here would be 1/32nd, 1/64th, and 1/128th. Okay? Sorry, I'm trying to make this so you can read it. And no, there we go. There are your fractions. So notice again, we're doubling the denominator. 1/16th, 1/32nd, 1/64th, 1/128th. So we're looking here at this. Now, we can do this, we can answer this question 2 ways. Okay? Fatal error of earth science teacher. I do not have a reference table with me. All right? But I know the answer to that. You may not, so you should look at your reference table. Off the reference table, the half-life of carbon-14 is 5.7 times 10 to the third, or 5,700 years. Now, if you notice, that's listed right there as 1 half-life. Okay, 5,700 years. Now notice, 2 half-lives, 11,400 years, and so on. One way you could do it is you could just keep adding 5,700 years onto this chart. That's one way to do it. The other way to do it is notice that 1 half-life is this, 2 half-lives is 2 times this, and so on. So you could go 7 times 5,700 years. All right, 7 times 5,700 years. And I would highly recommend going to a calculator at that moment in time, grabbing it. I've got to get mine open here, because I can't do that off the top of my head. Some of you might be able to, but I cannot. 7 times 5,700 years equals 39,900, which is answer D. Answer letter D. Okay, so notice again, this is our 128 that gave us the 7. That 7 came over here and went right there. 7 times 5,700 years gives us 39,900. All right. Question 4 looks similar again. Okay. It's similar to that, but we're going to be a little bit different here. It's kind of going backwards on this process. I need a little space. There we go. Now we can see everything. All right. So what is the amount of original carbon-14 remaining after 34,200 years? Now, I highly recommend, if you see a question like this, to fill the chart in. We are now at 1/16th, 1/32nd, and 1/64th. Okay? So these are the fractions here. All right, so what we need to figure out is which of these numbers times 5,700 years gives us 1/64th or 1/32nd or 1/16th. Figure out where that goes in. So it's kind of the opposite of the one we did here. We've got 34,200, okay? And here's a little trick. When you have a chart like this, usually they're asking for the last one. And just to double check, we divide that by 6. Usually. Don't guarantee it, but usually. There are my dogs again, going crazy. 34,200. Oops. 34,200 divided by 6 gives us 5,700. So this is our 34,200, and that gives us 1/64th. Again, you could add 5,700 and fill in this chart this way. I just think it's easier to go with the multiplication of this times the half-life. All right? That is... Okay, now this should look familiar. I actually created that little foldable to look at these types of questions. So, it says the diagram below represents rubidium-87. Which diagram represents the correct proportion of 87Rb to its decay product, Sr87, after 2 half-lives? Well, here's our illustration. Okay, 100%. Here's 1 half-life, here's 2 half-lives. So it should look like that. The small square is going to be still radioactive. The larger pieces are going to be stable. Okay, and that's really, really important. Because here, rubidium-87 is the radioactive part. Now, the only thing they do differently than I showed here is they put the boxes in the other corners. Okay, so this one here is 75% stable, and this is 25% still radioactive. Okay, so that gives us answer letter B. Okay, make sure this is the radioactive. If you have a question, can't figure it out, look at the reference table, page 1. It'll tell you exactly which one is the radioactive element or the isotope and which one is the decay product. Okay? 6. Graph below shows the radioactive decay of 50 gram sample of a radioactive isotope. According to the graph, what's the half-life of this radioactive isotope? Well, here's the thing. How much are we starting with? Okay, we're starting with 50 grams. And what phrase have we talked about all day? Okay, the word is half. Okay, half. What is half of 50? I'm insulting your intelligence by even asking you that question, but half of 50 is 25 grams. So, after 1 half-life, or what is the half-life? Where is it at 50 grams? Where is it at 25 grams? That's going to be right here. 25 grams gives us a period of time of 200 years. And again, what is that? What's the next 200 years? Puts us at 12.5. Next 200 years puts us at 6.25. Okay? And those are your percentages. Okay? The masses would be 12.5%, would not be 12.5, it would be 6.5, 25. All right, well, I am bad at math. I think I'm actually correct. 12.5 and 6.25. Those would be your grams. If you continue that every 200 years, it cuts itself in half. Apologize for the confusion. Hope you can figure out how I got back to where I was thinking. All right, moving on. All right, so it says an igneous rock contains... Okay. There we go. Now we can see. An igneous rock contains 10 grams of radioactive potassium 40 and a total of 10 grams of its decay product. During which geologic time interval was this rock unit most likely found? Well, I'm going to pause and come back with a reference table because I, even in my infinite wisdom on earth science, can't do this without a reference table.